So we're now going to start discussing the history of concurrency and parallelism support that's been available in Java. And this goes back kind of to the beginning of time, which is the mid-90s for Java. And you might know some of this, but if you don't, it's kind of fun to see how things have evolved. Java is a language that's been around for a long time, not as long as C++, of course, but it's been around for 25 plus years at this point in one way or another. So starting with the very first release of Java, which came out in the mid-90s, they had some foundational support for concurrency in the form of Java threads, which we've seen in our example of printing hello world, and also with respect to some things called built-in monitor objects. We're not going to spend a whole lot of time on built-in monitor objects in this class because it's really outside the scope of this course. However, if you're interested in learning more about built-in monitor objects, if you go to my YouTube channel, you'll see that I have a playlist from my concurrent object-oriented programming course, which I taught last spring, and we cover built-in monitor objects at length there. So if you're ever curious what these things are, that's a good place to go to look for it. The threads and built-in monitor objects that were available from the beginning in Java are part of what we call the Java execution environment layer, which is something like the Java virtual machine or the Android runtime. So it's basically baked into the underlying infrastructure part of Java. And these are typically implemented in C and C++ using wrappers around the underlying system calls available from the operating system that the virtual machine or the execution environment is running on top of. The focus for the foundational concurrency support is basically on multi-threading and synchronization primitives. So here's a couple of simple examples. You can see these examples in my GitHub repository in the simpleBlockingBound folder. And what we're going to do here is we're going to create a pair of threads, a producer thread and a consumer thread. And those threads are going to interact with each other via something called a simple blocking bounded queue. And as the name implies, it's a blocking bounded queue. That means that when the queue is empty, anybody who's trying to consume from the queue will have to block for the queue to be not empty. And if the queue gets full because it's bounded, then it means that if you try to put something in the queue, that you'll have to wait until the queue is not full. So not empty, not full are the conditions. And this is a way to allow threads to communicate by passing messages. In this model, we create an array of threads that share this simple blocking bounded queue. And then we have a loop that walks through that array of threads and starts both threads. They'll start up running. The producer will produce messages. The consumer will consume them. And then we go ahead and have the main thread, the one that started off the other threads, wait for the other threads to exit by calling their join methods. So very simple, very basic. We'll see the pros and cons to this in a moment. There's also some other foundational synchronization mechanisms available in the first version of Java and henceforth. And those include the mutual exclusion mechanisms available with Java built-in monitor objects, in particular synchronized statements and synchronized methods, which we show here, a synchronized statement. And there's also this concept of coordination primitives, the ability to wait on some condition to be true and to notify other threads or a thread when a condition may become true. So these are very foundational features. And monitor object is a pattern that's described in the POSA 2 book, which I wrote 20-some years ago. And it's a very fundamental pattern that's used quite a bit. The mechanisms that come out of the box with Java 1 and beyond are very efficient. They're written again in C and C++ for the most part, but they are low level and very limited in their capabilities. So they're simple, they're efficient, but they don't do a whole lot. And one of the consequences of the fact that they don't do a whole lot is if you start writing non-trivial programs with them, you will run afoul of all kinds of accidental complexities. And an accidental complexity is a complexity that arises due to some limitations with the software tools, languages, techniques, methods, processes, etc., that we use to build our programs, rather than something that's inherent in the domain of concurrent programming or parallel programming or whatever application domain you're working in. There's lots of inherent complexities, of course, with concurrency and parallelism, but these things are just due to the fact that the mechanisms that were available in the first version of Java were just very simple, maybe simple-minded is a good way to put it. So that obviously was not satisfactory. So with Java 5, which came out in the 2004 timeframe, so about a decade after Java 1 came out, they added a whole pile of new synchronization and threading mechanisms to Java. In particular, they added these things called the executor framework, which supported pools of threads, a whole slew of new synchronizers like semaphores and reentrant locks and reentrant read-write locks and condition objects, various kinds of blocking queues like array blocking queue and link blocking queue, atomics like atomic integer, atomic Boolean, atomic reference, and various concurrent collections like concurrent hash map. And these were all available in Java 5 and beyond. And these mechanisms focus primarily on so-called coarse-grained task parallelism. And you can see the link here for more information about what task parallelism is. And we'll talk in a second about what coarse-grain means. And coarse-grain in this context basically means it was expected to run on computers with a handful of multiprocessors or cores, maybe dual cores. That was about what they had back in that time frame. And all of the word task parallelism means is you can concurrently run various tasks at the same time, either logically, simultaneously by doing time sharing and time slicing of the threads over the handful of cores, or maybe running them on the cores in parallel, truly physically simultaneous. But the point is that it was fairly coarse-grained because there just wasn't a lot of cores to go around at that point. There's a simple example that you can see if you look at the link at the bottom of the slide, which is something called the Palantir Manager application. And what it does is it spawns a fixed size pool of threads using the executor framework. And each thread constitutes a being in the sense of beings from Lord of the Rings and Middle Earth, like hobbits and wizards and various other creatures like Sauron or Saruman and so on. And then these beings take turns gazing into Palantir, which were these kind of mystical seeing stones that behaved like FaceTime, I guess. It was the magical FaceTime. And this example also demonstrates some other more complex synchronizers like cyclic barriers that allow groups of threads to coordinate their interactions, and countdown latches, which do much the same kind of thing. And so these mechanisms allow pools of threads to coordinate their interactions to share a limited number of resources efficiently and fairly. And so that's an example of the kinds of things that you can do with the mechanisms that you get with Java 5. The mechanisms, the synchronizers and threading mechanisms, thread pool mechanisms available in Java 5 and beyond are very feature-rich. They're highly optimized. They're very well designed, but they're also somewhat tedious and error-prone to program because you have to do a lot of the work yourself. We're still living in the world of imperative, object-oriented programs where you tell the system what you want it to do, and it does it for you, but there's still a lot of complexity lurking there that will drive you crazy, much like the screen that we see here in this diagram. So that takes us up to about 2004. In the intervening decade and a half or so, a lot of cool new things have been added to Java. So one thing that happened with Java 7, which came out, I think, in the 2010-ish timeframe, was support for the fork join pool framework. And this is the beginning of the parallelism support. And a lot of these things are done in response to changes and enhancements in the underlying processor hardware. So the focus with the fork join framework was on so-called object-oriented data parallelism. And the idea is we take a big problem, we split it up into smaller chunks, and then we solve those chunks in parallel where the different parallel tasks work on different portions of the overall data that we're using as our input. So data parallelism is basically just saying we run the same task on different data elements in a larger collection by applying something called the split, apply, combine model. And we'll talk a lot more about split, apply, combine. You can see a paper down here below that introduces this, but this is really at the heart of the fork join framework and a lot of the other stuff that you'll find in Java parallelism. Here's a very simple example. This is the an example that uses a common fork join pool to search the complete works of Shakespeare to find famous phrases by the bard. So things like, neither a borrower nor a lender be, or my horse, my kingdom for a horse. So it goes and it looks in the complete works of Shakespeare in parallel using the fork join pool in order to identify whether there are matches there or not. This framework, the fork join framework, is very powerful, very scalable, but because it still lives in the world of objects and object orientation, it's a bit tedious to program directly. So it provides a really nice foundation for data parallelism and parallel processing, but there's still some complexity lurking because of the fact that you have to do a lot of the work yourself. So to address that issue, the Java 8 release introduced several new concurrency frameworks that addressed some of the limitations that were existing theretofore with earlier versions of Java. So this is what I would call advanced parallelism support. And Java 8 supports parallel streams and completable futures. These are two of the things we're going to focus on quite a bit in this course. So other stuff we talked about before is good for background knowledge. It's really the focus of my other course on concurrent object-oriented programming, but it's not something we're going to focus on here. So what's supported in Java 8 and beyond is functional programming that supports a couple different models of computation. One is functional programming for data parallelism and functional programming for reactive asynchrony. The data parallelism part is done through something called parallel streams, which we're going to focus quite a bit on, which is just a way of composing together a bunch of aggregate operations that transform flows of data and do various modifications and filters and so on to the data, and it does it in parallel. So here's a very simple example that we'll talk more about later, where we're going to take a list of URLs, ignore ones we've already downloaded that we've previously cached, and then we're going to download and transform or filter the images in parallel and then store them on our local machine in parallel. So this is an example of doing things in parallel. And you can see it's very concise, it's very declarative. Basically what this says is take the list of URLs and in parallel filter out the ones that we have already cached, so ignore the cached images, download the ones that aren't cached, apply the filters to transform the images, and then collect them all into a list. And even if you don't know much about Java streams, you could probably ferret out what I just said just by reading the names of the methods that are used in this particular example. And that's what's so cool about functional programming is it's very declarative. It says what you want done, which is the domain intent, as opposed to getting wrapped around the axle of how to do it. There's also support for so-called reactive asynchrony, and that allows you to be able to do computations that will run in the background asynchronously. Asynchronous just means without blocking the color for the purposes of this discussion. And when something is finished, then a mechanism, a proxy called a completable future is triggered, and then some other computation can take place. And this example here does the same work that the one did here, except this is doing everything asynchronously as opposed to synchronously, which is this one's done synchronously in multiple threads. This one's done asynchronously in multiple threads. And one of the consequences when we get to that part of the course, you'll see that the asynchronous version typically runs a lot faster than the synchronous version for this type of processing. And that really has to do with the fact that if you do asynchrony right, if you build the right abstractions into your runtime system, which Java has done, you can do a lot more processing with an asynchronous approach that maps nicely onto the underlying hardware characteristics, whereas the synchronous approach tends to incur a bit more overhead. They still both work very well, though. Now, the other thing that came along, and this actually came along sort of after Java 8 had come out, was support for something called reactive streams. And this was actually done with Java 9. So with Java 9, there was this concept of reactive streams that was defined. And then there's several frameworks that have come along and implemented the reactive streams model. And we'll talk more about reactive streams, but reactive streams is basically an asynchronous or potentially asynchronous publish-subscribe paradigm. And good examples of frameworks that implement this would be RxJava and Project Reactor. And what we do here is we use these mechanisms in order to be able to asynchronously download the images that aren't already cached in a list of URLs and process and store them in parallel. And we'll talk a lot more about how all this stuff works. It's very cool, and you'll get a chance to play around with this in some of the code. So the whole point of this discussion, especially the later features that were added to Java, was to try to strike an effective balance between human productivity, in other words, the time that people like you and I write code, write software, make us more productive by using these abstractions on the one hand, and balancing that with computing performance. And historically, there's been trade-offs. Historically, if you wanted to get computer performance, you used languages and platforms that were very low level, like C or assembly code. And you got things that ran fast, but they were very, very hard to develop, very hard to maintain, and so on. Conversely, if you wanted to use, historically, if you wanted to use higher level languages, then you got better human productivity because you could write them more quickly and without as many bugs, but they didn't run as well. And so the features that are available in real-time Java and concurrent Java and parallel Java and all these other features try to strike this balance between humans doing their job more effectively and more correctly, more efficiently as programmers without giving up the performance and throwing that out the window. And the thing that's made that possible, honestly, has been the continued improvement in processor performance, especially in terms of multiple cores, and of course the fact that network's getting faster, memory's getting cheaper, memory's getting more plentiful, and so all these advances in the hardware are motivating us to use more advanced software platforms and frameworks and patterns and tools, which used to cost you something in performance, but nowadays really don't. So that's good. So only people who are doing things like writing, the inner loop of a control system for a nuclear reactor temperature monitoring need to worry about using these very low-level mechanisms. More and more of this stuff can be done with the tools that come off the shelf, like Java, that will give you the benefits of performance without throwing productivity out the window and vice versa. The one downside with these more advanced frameworks, of course, is they can be overly prescriptive. They give you a model of computation that works very well if that's what you want to do. If you want to break your big problem up into smaller chunks and solve them in parallel, this stuff is fantastic. But not every program fits into that style of development. And so that's why these other mechanisms are still useful. Not everybody has the luxury of being able to do this stuff. And we'll talk in the next video about some criteria to think about when you're making a decision about which of these different features to use, when to use which approach. It becomes important architecturally to figure out what the right decision is for a given context. So that wraps up our discussion of the evolution of Java from concurrency to parallelism. The good news is you can kind of start at any point along the way and pick your technology and then be successful with it. But I think overall, as we'll see in the next lesson, you're probably better off nowadays sticking to the more advanced features because they give you a lot of benefits without incurring a lot of overhead.